Let's see how this substructure lemma naturally leads to a recursive search algorithm. The algorithm is recursive. I'm not going to bother to specify the base cases, which is when you're given a graph with at most one vertex, or whether you're given a value of k equal to 0 or 1. So let's assume that the graph has at least two vertices and that k is at least equal to 2. I wouldn't be surprised if this algorithm reminds you of some of the recursive implementations we discussed for various dynamic programming algorithms. And in the same way those algorithms exhibited exponential running time without memoization, we're going to see an exponential running time here. For all of our dynamic programming algorithms, we were able to cleverly organize subproblems from smallest to largest, thereby eliminating redundantly solving the same subproblems over and over again, yielding polynomial runtime bounds. Here, we're going to be stuck with the exponential running time bound. Obviously not surprising given that it's an NP-complete problem, but still, if you really want to understand this deeply, take this recursive search algorithm, try to come up with a polynomial time version. Try to come up with a small set of subproblems ordered from smallest to largest that you can solve systematically. You will be inevitably stymied in those attempts, but you'll better appreciate what's non-trivial about the recursive solution here. In step 1 of the algorithm, we pick some arbitrary edge u, v. Why is it useful to focus on an edge? Well, by the definition of a vertex cover, it has to include either u or v. So that's our initial clue. We're going to proceed optimistically. We're looking for a vertex cover of size k, so let's assume one exists. What does the substructure lemma tells us? It says that if such a solution exists, then necessarily either gu or gv or both themselves have small vertex covers of size only k-1. Moreover, it's a simple matter to extend such vertex covers to a small one for g. You just augment them by the missing vertex. So let's first adopt as a working hypothesis that G sub u has a small vertex cover of size only k-1. Let's recursively try to find it. If our recursive search comes back with a solution, a vertex cover of size k-1 for GU, we're good to go. We just augment that by the vertex u, and that's our vertex cover of size k for the original graph G. If that recursive call fails to find a small vertex cover, we say, oh, well, then it must be that V is the key to getting a small vertex cover. So we do exactly the same thing. We recursively search G sub V for a vertex cover of size k-1. If the second recursive call also fails to find a small vertex cover, one of size only k-1, then by the substructure claim the other direction, we know that the original graph G cannot have a vertex cover of size k. If it did, the substructure lemma tells us one of the two recursive calls would have succeeded. Since they both failed, we conclude correctly that the original graph did not have a small vertex cover. The correctness analysis is straightforward. Formally, you would proceed by induction. So the inductive hypothesis would then guarantee the correctness of the two recursive calls. So on the smaller subproblems GU and GV, the recursive calls correctly detect whether or not there are vertex covers of size k-1. The substructure lemma guarantees that we correctly compile the results of the two recursive calls into the output of our algorithm. So if one of the two recursive calls succeeds, we're good to go. We just output the vertex cover of size k as desired. And this is the crucial part. If both of the recursive calls fail, then by the substructure lemma, we know we correctly report fail. We know there is not a vertex cover of size k or less in the original graph G. So let's analyze the running time using an ad hoc analysis. Let's think about the number of recursive calls that there can be over the entire trajectory of the algorithm, or equivalently, the number of nodes in the recursion tree generated by the algorithm. And then we'll come up with a bound on how much work is done in a given recursive call, not counting the work done by its recursive subcalls. And now the cool part, and this is really where the role of a small value of k comes into play, is that each time we recurse, we subtract 1 from the target size of a vertex cover that we're looking for. Remember, if we are given as input the parameter k, each of our recursive calls involves the parameter value k-1. So what this does is limit the recursion depth, or the depth of the recursion tree generated by this algorithm, to be at most k. Initially, you start with k. Each time you recurse, you decrement it by 1. You're going to hit base cases by the time k is around 1 or 0. Putting those two observations together, branching factor bounded by 2, recursion depth bounded by k, the number of recursive calls in total over the entire lifetime of this algorithm is going to be bounded by 2 to the k. Moreover, if you inspect the pseudocode, you see that not a whole lot of actions going on other than the recursive subcalls. So even with a very sloppy implementation where you have to construct G sub u and G sub v from the input graph G, even if you do that crudely, you're going to get a linear time bound, big O of m work per recursive call, not counting the work that gets done later by the recursive subcalls. So that means an upper bound on the total amount of work done by this algorithm is the number of recursive calls 2 to the k times the work per call m, 2 to the k times m. Now this running time, you'll of course notice, is still exponential in k, but of course it has to be exponential unless we intend on proving p equals np. Don't forget the vertex cover problem is np complete. So what have we accomplished? We had a trivial exponential time algorithm by brute force search earlier. Why did we go through this rigmarole to come up with a second algorithm with this exponential runtime bound? Well, this is a qualitatively better running time bound than we had before with naive brute force search. Here's two ways to see why this running time bound is qualitatively superior. So first, let's just inspect this running time from a mathematical perspective, and let's ask how large can we take k while still having a polynomial time algorithm. Recall that our naive brute force search algorithm, where you just try each subset of k vertices, ran in time theta of n to the k, and so that's polynomial time if k is constant, and it's super polynomial time if k is bigger than a constant. For this running time bound 2 to the k times m, we can let k grow as large as log of the graph size and still have a polynomial time algorithm. So now let's segue from these mathematical bounds to thinking through actually implementing these algorithms and running them on actual data. So for the naive brute force search, you've got this running time of n to the k. And even for a relatively small graph, let's say n is maybe 50 or 100, you're not going to be able to run this naive brute force search algorithm except for extremely small values of k. 3, 4, maybe 5 if you're lucky. So naive brute force search has very limited range of applicability. So by contrast, our smarter search algorithm can accommodate a noticeably larger range of k's. So remember, the running time here is 2 to the k times the graph size. And so even for values of k up to 20, for many networks of interest, you're going to be able to implement and run this algorithm in a reasonable amount of time.